Okay, hello everyone. Welcome to the last information theory session. We will have 3 great talks in the session, and our first speaker is Satvik Singh from Cambridge University. He will talk about information transmission under Markovian noise. Satvik, please.
All right, thanks for the introduction. Thanks for coming, everyone. I hope you guys are not too dead by now. I know I kind of am. But anyways, I will talk to you guys about information storage and transmission under Markovian noise. So this is joint work with Nilanjana, Omar, Miza, and Mostafa, none of whom are here. Okay, let me begin with the basic setup. Actually, before this, can I just get a show of hands? How many people here actually do error correction by any chance? Is there anyone? Okay, just wanted to, I hope you guys will not be too disappointed. Anyways, so we will look at this physical memory device. So we have some kind of an open quantum memory which we want to use to store data, logical information. This memory is experiencing some noise in time, which we assume is going to be Markovian. So we model this by some kind of a discrete Markov semigroup, which is nothing, basically just a channel, and we just apply it over and over and over again, and the number of times it's applied is our parameter for the time. And after this process, we encode initially at time t equal to 0 our logical data into some error correcting code. We let the noisy process do its thing, and at time t, we do some decoding, try to recover our information back. And so this is the setup. And this kind of a setup encompasses 2 scenarios. So first one is the passive error correction scenario, where you just encode at t equal to 0, let the noise do its thing, it's just noise, and then you do all the recovery at the end. So this is the passive setup. We can also have some kind of an active setup where you periodically try to correct for errors. You have some kind of an engineered error correction mechanism that periodically checks what's going on, detects the errors, and try to correct them as the noise is happening. So this is the active setup, but we kind of just think of this as some QMS, some discrete Markov semigroup. And since we are in an information theory session, we'll just not care about what exactly is the error correcting code and so on. We just optimize over all error correcting code. We are just happy as long as it exists. We will assume no gate errors, no nothing, all the encoding, decoding, everything is perfect, Shannon theory. So I guess you guys get the point. And I should emphasize that this is one-shot framework. So the physical memory, it might be comprised of like 1,000 qubits, whatever, but we don't assume any sort of assumptions. There's no assumptions whatsoever on the noise. So it can do arbitrarily correlated things on your qubits. There is no IID assumptions. No, it's just a one-shot framework. Okay, so as I said, we're going to optimize over all error correcting codes. So this gives us the notion of a capacity of the noise. So for any noisy channel, you can define its capacity, the quantum capacity, as the maximum number of qubits that you can store for this noise. So the supremum is over all possible error correcting codes. And this epsilon is the parameter that we use to quantify how much error you allow in your recovery procedure. So you might not want to recover things perfectly. You just allow some error epsilon in your recovery. So this is one-shot epsilon error capacity of a noisy channel. And similarly, if you want to store classical data, then you optimize over all classical codes, where now the recovery would be some kind of a measurement. And again, the error epsilon quantifies how much, what is the infidelity in your recovery procedure. Okay, so what's the question that we ask and try to answer? So basically, how much data can you store in your memory for time t? So more precisely, we want to study how does this capacity function that we have, it behaves, how does it behave as a function of the noise that you have, the time t, error epsilon. And in particular, we'll be interested in what is the long time limit of this, what is the limiting value, when does it go to 0? So for what kind of noisy processes is the noise too severe that it doesn't allow you to store anything essentially for arbitrarily long time? How fast is the convergence? Can you compute this limit efficiently? Is it additive under the noise? Things like that. So this is the basic setup, and these are the questions that we'll try to answer by the end of this talk. So basic obstacles that one has in Shannon theory is that you can define these capacities, but there's this complicated optimization over all error correcting codes. These are like hard to compute, so you can't essentially do them, like work with them. They're not nice functions, and they have these also extreme non-additivity sort of behaviors. So it might be the case that you have two noisy channels for which you can't store anything, but when you tensor product them, you have some kind of you gain some storage capacity because of entanglement and things like that. So these are like the usual obstacles that one has in Shannon theory. But we'll try to see how this is not really an issue when you are looking at the long time limit of these things. Okay, so what can we do? So we want to store information in our memory, and we want to store it in such a way that is shielded from noise, that you can recover it back. So the first natural thing to do is probably, okay, let's look at the fixed point space. This is by definition the space where nothing happens, noise doesn't do anything, so it's a very natural candidate to consider. And it turns out that this space has a nice algebraic structure. For any CPTP map, you can kind of decompose the underlying Hilbert space into these direct sum structure, and the fixed point space has this nice matrix block algebraic structure. So these are the blocks that we will use to store our information in. And since by definition everything in this space is fixed, you can trivially recover it because nothing is happening. So we get these lower bounds, so these achievability results that there exists this error correcting code. You can just encode your information in these blocks, and it is always recoverable because nothing is happening in this space. So for quantum capacity, you just choose the size of the maximum block, and this gives you this lower bound. For classical capacity, you can encode things in your diagonal of each of these blocks, so you can store sum over k these dimension number of messages. But then the question is this the optimal thing to do? Maybe there's something better. And it turns out that that is the case. This is not the optimal thing to do. And the easiest way to see this is like looking at this classical example where it's like a cyclic permutation channel. It doesn't do anything. It just shifts things around. And for this channel, you can easily see that the fixed point is just the uniform distribution. It's just a unique fixed point. So these bounds are trivial. They don't tell you anything. But however, there is no noise, nothing is confused, it's just shifting things around, so you can send log d bits of classical messages through this channel. So this is not storing information in the fixed point space is not the optimal thing to do. What's the next natural candidate that one can consider? So the next obvious choice is the peripheral space, the so-called peripheral space of the noise. So let's just recall that since you have a CPTP map, all the eigenvalues are inside the unit disk in the complex plane, and as t goes to infinity, morally speaking, everything inside the peripheral, the eigenvalues inside kind of just decay away. So the space that is relevant in the long time limit is this so-called peripheral space, which is just this span of all the eigenspaces corresponding to the peripheral eigenvalues. And again, you can show that this space also has this nice algebraic structure. It has these nice matrix blocks, but this is now a larger space. So the fixed point space is somewhere inside this. So we get, and how does the noise act on this space? So it's not as trivial as the fixed point, but it's not too bad as well because the noise can only just shuffle these blocks around. It doesn't decohere anything. So this is kind of like a decoherence-free space of your noisy process in some sense. So you can show that there exists this permutation, and the noise kind of just shuffles these blocks around up to some unitary conjugation. So whatever you store in these blocks, it doesn't decohere, it can just shuffle amongst each other, and so you can do the recovery, and you again get these lower bounds, but these are better because this is a larger space. And now we ask the same thing, is this the optimal thing to do as t goes to infinity? And it turns out that it is the case, and this brings me to my main results. So for any noisy channel, you fix the error with which you allow the recovery, and the lower bounds we just saw that these are the achievable lower bounds, and conversely, in the limit of t going to infinity, this is the optimal thing to do. So you can't do better than just storing information in your peripheral space. And the error that you allow in your recovery, it just gets this additional log 1 over 1 minus epsilon term, which just goes to 0 as epsilon goes to 0. So in the limit, if you want to do things perfectly, epsilon equal to 0, these two bounds kind of collapse, and you have the exact formula for what you can do. And the nice thing about this is that these formulas are efficiently computable. So it turns out that you can come up with an algorithm that will take your noise and compute the structure of the peripheral space efficiently. So these capacity formulas are efficiently computable. There's a poly-D algorithm that will give you the structure of this peripheral space for any given noise. So this is very nice because usually these formulas are not nice. I mean, they are computationally hard to compute. So I mean, this is a nice property that in the limit of t going to infinity, all these things are efficiently computable. Let me spend a couple of minutes on the IID setting now. So let's say our physical memory is comprised of n qubits, let's say, and each qubit is experiencing the same sort of Markovian noisy process, and which is modeled by this psi semigroup. And now we kind of want to see how many qubits can you store in your memory per qubit, and this is kind of like the rate at which you can store information in this memory. And so the quantity of interest is this thing in the middle. So this is precisely the maximum number of qubits that you can store per qubit in your memory in the limit of time going to infinity. And the nice thing about the IID setting is that you can show that the peripheral space of the noise is multiplicative under tensor product. So all these capacity formulas become additive. So the rate at which you can store information, the optimal rate is again given by this log max over k dk, the largest block dimension. And notice that this formula is true for all epsilon and for all n. So if you just take the limit as n goes to infinity and you fix some epsilon, you always get the same rate at which you can store your information. So this is what is known as the strong converse property. So the rate at which you can store things, it is independent of the error that you allow in your recovery procedure. So this is normally not the case. It is expected that if you allow more error in your recovery, then the rate at which you can store things become better. So there's some kind of a trade-off usually between these two quantities. But in this case, in the long time limit, it turns out that you have the strong converse behavior in the sense that for every fixed error, the rate at which you can store information is the same, and it is given by this maximum block of max decay of the peripheral space of the noise. Just to tweak it slightly, another way to look at this is that if you fix your rate at which you're storing things, then you can just slightly massage this inequality to see that the probability with which you will successfully recover your information will go to zero exponentially fast if you try to store at a rate above this log max over k dk. So this is another way to put this strong converse behavior. All right, so this is the IID setup. Let me quickly tell you about what happens in the classical case. So classically, you have some stochastic noise, and you have a Markov chain, essentially, some input symbols, and you have the stochastic matrix, which govern the transitions. So since all the notation I used was for quantum channels, let me just embed the classical into the quantum like this. So this is just a channel that completely decoheres everything on the off diagonal, and on the diagonal, it just acts like this stochastic noise. And for this channel, the space, the peripheral space must be commutative, because if not, then you can store a qubit for this completely decohering channel, which is impossible. So the sum over dimensions is just this dimension of the peripheral space, which is nothing but the number of peripheral eigenvalues of your noise, of your matrix. So, and it turns out that this number of peripheral eigenvalues in the stochastic classical case has a nice combinatorial interpretation. So what you can do is kind of, you have this vertices, your input symbols, you have some noise which governs the transitions. You can partition your set of vertices into these disjoint communicating classes. So these blobs represent these classes, communicating classes, meaning that inside this blob, any pair of vertices, there is a path that leads from one to the other. So this is like strongly connected in some sense. But some of these classes might be open in the sense that there might be a non-zero probability of you transitioning out of this class once you're inside. And some of them are closed in the sense that once you're inside this class, then you're just trapped forever. So these closed classes, you can think of them as their own noisy process, independent of everything else. And so these closed classes correspond, will give some contribution to the peripheral eigenvalues. And inside the closed class, you have further structure. You can further partition your vertices into k disjoint classes. And you can show that the noise essentially just shuffles things around cyclically in this class. So if you store your classical data into these k disjoint blobs within a closed class, you're just, again, in the case that I mentioned earlier, just cyclically permute things, and you can recover everything back. So the formula for the maximum classical data that you can store for this classical case is just you take all the closed classes, you look at the period of each class, and you sum over that, and this is the best you can do. And I should note that classically, there are efficient algorithms which can compute these decomposition into communicating classes. So you can, all of this is very efficient. You can compute this. And in comparison with the finite time case, this single shot, this C0 phi A by itself is NP hard to compute. So there's like clear distinction that things are becoming easier in the long time limit. And similar things can be done for quantum channels as well. Like this, in this case, your classes would be like some subspaces of your Hilbert space, but I don't know much about this actually, so I'll not go in too much into this. Okay, quickly, let's just see when can you, for what kind of noisy processes can you at least store something for arbitrarily long time? So we have the following, this result. This is an easy consequence of our main theorem. It just says that for any noisy channel, in the limit of t going to infinity, the capacity will vanish if and only if the space that you have, the peripheral space, is commutative. All these blocks are one-dimensional, and this is equivalent to saying that the noise becomes entanglement breaking in the limit. And the typical example of such kind of a process is like a dephasing sort of noise, where you just reduce the magnitude. You fix some bases. The off-diagonal things are reducing in magnitude, and in the limit, you just project onto the diagonal algebra. You become entanglement breaking. And for classically, you can't store any classical data in the long time limit if and only if your evolution is mixing. So there's a unique fixed point, and in the limit of t going to infinity, everything is just squished to this one single point. So you can't store any classical data arbitrarily long, even one bit. And typical like amplitude damping sort of noise, where everything is dampened, it's going to this base ground state. Depolarizing sort of noise, where everything is getting sent to the maximally mixed state. These are typical examples of such kind of processes. Okay, I have 3 minutes. Let's talk a little bit about the convergence behavior. So what you can do for any noisy channel, you can always do this Jordan decomposition, and you can combine the Jordan blocks for the peripheral eigenvalues into this asymptotic part of the channel, and you can write down the projector onto the peripheral space by summing over the projectors the Jordan blocks of peripheral eigenvalues. And then you can get like a spectral convergence estimate. So as t goes to infinity, the channel, the distance of the channel to its asymptotic part, it exponentially goes to 0, where the exponential rate is like this governed by the spectral gap. So in finite dimensions, there's always a spectral gap. You just remove the peripheral eigenvalues, and then you see what's the largest magnitude of the eigenvalue that's left. And as t goes to infinity, the channel, the semi-group will converge to its asymptotic part like this. And you can show that for any sort of a noisy process, as long as the spectral gap is not too wild, in the sense that it doesn't go to 1 quickly, this asymptotic behavior starts to kick in after time of the order of d squared log d. So it is at this time scale that we would expect the capacities to be close to the asymptotic quantities that we considered briefly. And this is the second. This brings me to the second main result. So just to recall, we had the peripheral space. We just saw that the achievability bounds are true for all time. So you store information in your peripheral space, you can recover them at all times. So these lower bounds are true for all time t. And then conversely, if your time is of the order of d squared log d, then you can use the spectral convergence estimate to show that the capacities will be also upper bounded like this. Okay, brief proof steps. Essentially, you want to deal with these one-shot classical capacity. The first step is use some sort of continuity sort of bound on these one-shot capacities to shift this the problem from the phi to its asymptotic part, because it's easier to handle. And then you use some data processing to further shift the problem from the asymptotic part of the channel to this projection channel, which is again nicer to work with. Then you do the usual connection of this one-shot channel capacities with hypothesis testing to get this some sort of a bound on what is the best that you can do. And essentially, the point is that for these projection channel, these entropic quantities are easier to compute because you have a nice form of this channel. It just projects onto these matrix blocks, so you can compute all of these entropic expressions nicely. So in this step, we use we transfer from the hypothesis testing problem to the usual relative entropy by using entropy inequalities and things like that. And the final step is where you utilize the fact that since you're projecting onto this block structure, so you can compute these entropic quantities nicely. Okay, almost out of time. Conclusion, this is the take-home slide. Just the summary. You have a noisy channel. We wanted to study how these capacities behave with respect to the noise, time, and epsilon. And the answer is that for all time t, these capacities are lower bounded by the maximum block of these dimension of the peripheral space. And so the moral is that you store information in this peripheral space. It is kind of shielded from noise. The noise can only just shuffle things around. You can recover everything back. And if you wait for long enough time, which is of the order of d squared log t, then this is also the best that you can do. And so we have these converse bounds. And bonus is that these formulas are efficiently computable, which is not the case usually in Shannon theory. They're additive. All the obstacles that we talked about in the introduction, they kind of just go away, and in this long time limit, everything becomes nice and simple. Also, the double bonus, strong converse holds as well as t goes to infinity. Finally, briefly, future problems to consider. Can you talk about better convergence estimate if you have more knowledge about your noise process? Maybe you can do more fancy active correction where instead of a fixed recovery procedure, you allow some classical memory and you do things adaptively. What happens if your noise is not Markovian? I don't know. And what happens if like you're going away from Shannon theory now, like your encoders and decoders are not perfect, so can you say something in that setting? Okay, but I'm almost out of time, so thank you for your attention.
Okay, we have a couple of minutes for questions.
Hey, thanks a lot for the talk. Do you really need the continuity estimates, or can't you get away with like some semi-continuity statement for the capacity? Because in the end, you are taking anyway the limit, right? So do you need the explicit continuity estimate, or could you?
I mean, this is like the one shot. It's not really a continuity estimate. You're just saying that if two channels are close to each other, if you can send something with error epsilon with one channel, then the same kind of strategy works with error epsilon plus whatever closeness distance that you have for the other channel. This is kind of like a modified continuity continuity estimate. It's not exactly like a continuity sort of bound.
Right. Okay, I see.
Yeah.
Thanks.
Any questions? Actually, I have one question. I'm wondering when the rate is below the capacity, then do you know the error decays exponentially? Because you showed it strong converse.
Yeah,
right?
yeah.
But if the rate is below.
I think so. I'm not completely sure, but because we have these.
From the upper bound, it's clear,
Yeah. I don't know.
Sure.
Yeah, because the achievability part, everything happens exactly. Like, if you store information in your periphery, you can recover it exactly with epsilon
so it
equal to
means
0.
like zero error.
It's like zero error. So all four of these achievability can be done exactly. So yeah, I don't know that.
I see.
Thanks for the nice talk. So here you assume that as time flies, your noise always stay unchanged, right? So it's a fixed noise. So what if but in practice, I believe that the noise model will fluctuate along the time. So what if you consider this case?
Yeah, I mean, so I don't know. This is the non-Markovian question that I have.
Yes. No Markovian, yeah.
Yeah, I mean, if you have some kind of, if environment has some kind of a memory, then I think even these capacities need not even converge to some value. They can kind of just even shuffle around, and you can do like some weird things where you need not even converge to some specific things. So I don't know what would be the right framework to actually phrase this problem in, and how do you tackle it. But yeah, this is an interesting direction to pursue.
Okay, thank you.
Okay, let's thank Satvik again.